Let's start by building out a table of possible values of s. M and k can be greater than or equal to 2. We'll have m go down this column and k go across. And since we're interested in f of 30, we'll only fill in the values that are less than or equal to 30. So with a base of 2, we get 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16. With a base of 3, we get 9 and 27. A base of 4 gives us 16, and a base of 5 gives us 25. So these are the numbers we have to work with to sum to 30. First, let's take a look at this first row of numbers. These are the powers of 2, where k is greater than or equal to 2. So these are all of the binary numbers except for the last 2. This means that whatever is to the left, let's say the 4 digits A, B, C, and D in binary, that's going to be represented by the numbers in this first row. And these are all going to be multiples of 4. If we write this number in base 10, we'll have A times 2 to the 5th, B times 2 to the 4th, C times 2 cubed, and D times 2 squared. We can factor out 4. Inside the parentheses, we can write this as a 4-digit number in base 2. These are all the numbers from 0 to 15. So we can add any combination of these first row numbers to get all the multiples of 4. Multiples of 4 leads us to ask, what are the mod 4 residuals of these remaining numbers? So in mod 4, 9 is equivalent to 1, 27 is equivalent to 3, and 25 is also equivalent to 1. So some combination of 1 or more of these 3 numbers gives us all of the residuals of mod 4, including 0 if we don't use any of them. So our strategy to find these sums is to write n as the sum of one of these 3 numbers, so that what remains is going to be a multiple of 4. So we're going to divide up s into 2 sets, one of which is going to be our first row numbers, from which we can get any multiple of 4, and then these 3 remaining numbers, from which we will subtract from n in such a way as to leave behind a multiple of 4. First of all, by inspection, we can see that f of 30 is equal to 0 because we can't sum any of these numbers to get 30. Now for part B, we're going to divide up our numbers according to their mod 4 residual. So for example, if n is a multiple of 4, then it can be written using elements from this first set. If n is 1 more than a multiple of 4, then we can write n as the sum of 9 and its remaining number to leave a multiple of 4 behind. Writing it this way, we have 9 is in s, and we have n minus 9 is a multiple of 4, so we can use these powers of 2. Let's look at an example. Let's take n equals 33. Since 33 is 1 in mod 4, we'll write 33 as the sum of 9 and the remaining number 24. 24 is a multiple of 4, so we can write it from those powers of 2. That's 16 and 8. In this case, we have to have n greater than 9. Let's see what happens when n is equivalent to 2 in mod 4. If we take n and subtract 9 and 25 and replace them with their mod 4 residuals, we'll get a multiple of 4. In this case, n has to be greater than 34. Let's try as an example 34. This is the sum of 9 and 25. Another example is 38. We write this as the sum of 9 and 25 and 4 more, which comes from our first row in our table. Our last case is when n is equal to 3 in mod 4. If we subtract 27, then we'll get a multiple of 4. So n minus 27 is equivalent to 3 minus 3, or 0. If n is equal to 27, we get our sum. But when we get to n equals 30, we earlier showed that f of 30 was equal to 0. So in this case, our first valid value of n is n equals 31. This is equivalent to 3. So we would take 31 and write it as the sum of 27 and whatever remains, which will be a multiple of 4. In these 3 cases, we show that our minimum value is 31. When n is greater than or equal to 31, depending on its mod 4 residual, we can use this algorithm to subtract some combination of 9, 25, and 27, leaving behind a multiple of 4, and we can use this part of our set S to build out our sum. Let's go on to part C. Since we need to have at least 3 ways to build out our sum, let's add to our table of possible values of S. M is the base and K is the exponent. Our first row makes our multiples of 4, and we'll do this for all n less than or equal to 100. With a base of 3, we get 9, 27, and 81. 4 is going to duplicate the first row, so I won't fill this in. 5 is going to give us 25 and 125. 6 will give us 36. This row of the powers of 8 is also going to be duplicate. And finally 100. Let's split up our set S, again in the powers of 2, and these other numbers in sorted order. We've already shown that for n greater than or equal to 31, we can get at least one sum of n using some combination of these 3 numbers, or none of them if it's already a multiple of 4. That will leave remaining a multiple of 4 from which we can add some combination of numbers from this first set. We're interested in the situation where we can get 3 additional sums and be guaranteed of that. This is a situation where we can subtract 36 or 49 or 81, the next 3 numbers in our set, creating at most 3 more sums, and then another one when we subtract out these numbers using these first 3 numbers as we did before. When f of n is now guaranteed to be greater than or equal to 4, we can look back from there and find the largest integer where f of n is equal to 3. Because we're guaranteed at least one solution when n is greater than or equal to 31, let's add 31 to 81 and see if we can't get 4 sums. Also notice that once we get to 112, we also have at our disposal 100 with which to create a sum. So I'm pretty confident that f of 112 is going to be greater than 3. Let's use our algorithm. First of all, 112 is a multiple of 4, so we know that we can write 112 using just the numbers in our first row. That's 64, 32, and 16, and that's our first valid sum. Let's now write 112 as the sum of 100 and some other number. 12 is a multiple of 4, so it can also be written using our first row numbers, 8 and 4. That's our second valid sum. Let's now write 112 as the sum of 81 and something else. That's 31. And we showed earlier that since 31 is equivalent to 3, we can write it as the sum of 4 and 27. That's our third solution. Let's subtract 49, and we're left with 63. 63 is equivalent to 3, so we'll write this as the sum of 27 and 36. Since 27 also has a mod 3 residual, we're left with a multiple of 4, which we can write as powers of 2, 32, and 4. That's our fourth solution. For fun, let's go ahead and write 112 as the sum of 36, and we're left with 49. 49 is one more than a multiple of 4, so for those we pull out 9, and we're left with 40, which is a multiple of 4, which we can write as 32 plus 8, giving us another solution. So it looks like f of 112 is equal to 5, and I think it's pretty clear that for larger numbers, we're going to be able to get 4 sums. Let's see what happens when n is equal to 111. 111 is equivalent to 3 in mod 4, so let's first begin by using our algorithm from part B. We'll write 111 as the sum of 27 and 84. Because 27 is also 3 more than a multiple of 4, that's going to leave behind a multiple of 4, which we can write with our first row numbers, and that's our first sum. Let's try 111, subtracting out 100. That leaves us with 11. 11 is less than 31, so we're not guaranteed a sum. But if we take a quick look at the numbers that are less than 11, we see quickly that we cannot get that sum. F of 11 is 0, so this is not a valid sum. Let's take 111 and subtract 81. This leaves us with 30. In part A, we found that f of 30 is equal to 0. Let's write 111 as the sum of our next number in our set, 49. That leaves 62. 62 is equivalent to 2 in mod 4. Again, for those numbers, we pull out our 2 numbers that have 1 mod 4 residual. That's 9 and 25, which leaves behind 28, our multiple of 4, which we can get by adding up 16, 8, and 4. This is our next valid sum. Let's subtract our next number, 36. This leaves behind 75. 75 is equivalent to 3. So let's pull out 27, which will leave our next multiple of 4. 48 is 32 plus 16, and that's our last valid sum. So we have f of 111 is equal to 3. 111 is our largest element in that set of numbers that has 3 valid sums. That makes this set finite and also non-empty. If you'd like me to solve any other contest problems, please leave them in the comments.